Hello, and welcome to emulating Risc-V in a high level language. And in this episode, we're going to be looking more closely at assembly language. Now, so far in the series, I've been lying, or b- I've been deceiving you, I should say, because although I've been saying things like assembly language, the code that we've been writing so far has always been C sharp. Every single line of programming code has been in C sharp, even though it has been expressed as a machine language. But I've reached the point now where I want to take the step and into actually writing real assembly language. But in order to make use of this assembly language, I need also to write a piece of code that can take the assembly language and convert it to machine code. Now, in the existing code base, this task is rather easy. We are piggybacking on the C sharp compiler, and it does all the heavy lifting for us. It takes the program code, which is written in C sharp, and then turns that all into assembly language. What we're going to do now is we're going to actually write a assembler, which takes assembly language written in its own syntax, and then it turns that into machine language. I also want to take the opportunity to point out that the source code for all of the episodes that we've seen so far is available out on the URL that is in the description below. So let's take a look at the problem at hand. We have this program that we were able to get working last time. It's all in C sharp, as you can see. And this is not real assembly language. I mean, it looks assembly language-ish, but in reality, this is all C sharp. And this is also not what real assembly language looks like. So what I'm going to do is I'm going to take this program and I'm going to translate it into assembly language. And then we will then write a program that can take this assembly language and uh, perform what the assembler is doing here. That is translated into machine code. So where does our program begin? It begins at line 10. Let's start there. And then let's grab a few lines of code. It's quite a few lines of code. So right about there. So there's our machine language program. And let's call this, let's create a new file for this. And we'll call it, well, it was called echo.asm. This is the echo program. So here we go. So first things first, in assembly language, there are conventions just like there are in C sharp or any other high level language for that matter. And so we have to define what those conventions are. Like what does a program, a syntactically correct program consist of? One of the first things we can do is change the comment character. By tradition, in most assembly languages, the semicolon has been traditionally used to introduce a line comment. So let's replace the double slashes that we've been using, which are C sharp, line comments with a semicolon, which is the assembly language equivalent. Now, this is naturally, if you were to design your own assembly language, you could use whatever character you prefer. Actually, let's undo that. Let's first remove any semicolons that we might have, because the semicolons are going to be comment characters. So we'll remove all the all the semicolons and replace them with nothing. And now we replace the comment characters with a semicolon, like that. All right, so the next thing we want to do is find all the places where we explicitly type m.label. Those are going to be our labels, and so what we'll do is we'll replace everything that is written this way and replace that with just $1 and then or the label string itself. Let's strip off the double quotes and let's see if that works. Yep, that looks good. Except here, but that's okay. We can fix this. Okay, nice. So that was the first transformation. The next thing that we'll want to do then is replace all the places where we say m dot something and replace those with the simple something. So m dot and then some word, and we'll want to replace everything that's inside parentheses, and let's do that. And that will be replaced with $1 space dollar. Let's put a few more spaces. $2. So what I'm doing here is just textual transformations. I'm just making these text changes. Yeah, this looks good. Let's just do them all. Okay, good. And then what else? We still have some labels left. Let's get rid of those. So find anything um, that is double quoted and strip it, making sure we don't destroy our strings at the end of the program. So let's see. Oh, not that one. I want to keep that one. So let's find the next. This one. Okay, good. All right. So this is what a typical assembly language program would look like. So the syntax is very simple, as you can see. There are no complicated expressions at all. Um, we do have these operations. We need them for our relocations. So we'll keep those. And now we have transformed our program from C# to assembly language. Now this assembly language is a particular dialect that I've invented myself. It doesn't correspond to any official Risc-V assembler, but it does the job. It represents the machine code instructions as human readable mnemonics and their operand values. So what would it take to actually write a program that takes the contents of this text file and turns the contents into machine code? Well, we'll divide the work into stages. The first part is going to be to go through the contents of the file and then splitting it apart into pieces that are more easy to understand. So what we're going to do is we're going to write something called a lexer, and a lexer is a program that takes text like this text file and chops it up into tokens, which are sort of the smallest symbols or smallest pieces of information of this file. Before we can write a lexer, though, we have to identify what those tokens are. Like, what kinds of entities do we have in our file? What kinds of symbols do we want to recognize when we parse this file? And so let's write down a few of them. First of all, comments. So we want to be able to identify comments. And what is a comment? Well, it begins with a semicolon and then it goes on all the way to the end of the line. That's a comment. Um, well, empty lines, we should be able to recognize those and ignore them. And then we want to recognize symbols. Actually, let's go back here and say a comment. It begins with a semicolon and then is followed by anything. This is a regular expression that recognizes a comment. Then we have numbers. We want to recognize the numbers. So what does a number look like? Well, it's going to be, first of all, there may be an optional minus sign at the beginning. So maybe there's a minus sign, and then the numbers from 0 through 9 repeated 0 or 1 or more times. So an optional minus sign followed by any number of digits, that's a number. And um, we are going to treat commas and spaces and tabs as white space. So that's either a comma, a space, or a tab. Those are all white space, and those will just be separators. We'll be ignoring them. And then we have a colon, of course. That's the symbol that terminates a label, just like in the C sharp or any of the C language family languages. So after a symbol and a colon, we know that we've seen a label, and that's easy enough. It's just a colon. And we'll want to recognize parentheses so we can handle constructs like this. So we'll want to have a left paren, which is just a simple left paren, and then a right paren, which is a right paren like that. Okay. What other symbol types do we have in our program? We have strings. So let's add support for strings as well. So a string is a double quote, and then we follow it by either any character that is not a backslash or a backslash followed by and some some characters that we will treat specially. So we'll want to treat backslash n, that would be our new line, backslash r, that would be a carriage return, maybe support for tab, and also we want to be able to support double quotes. And finally, how about a backslash to escape a slash itself? If you're familiar with any of the C programming language family languages, then you'll recognize these as the typical tokens that you'll find in a string, like slash r, slash n, and slash slash, and so on. Um, I also want to add support for binary and hexadecimal numbers. So binary number, um, the way we're going to implement those is we're going to start with 0b. So the 0b prefix is a marker that says I'm starting a binary number, and then we allow only ones and zeros. So that's a binary number. And then a hexadecimal number is going to be 0x followed by any digits from 0 through 9 and any number from 0 through or A through F and capital A through capital F. So if we can recognize tokens for all of these different entities, then we should be able to consume one of these files. But I've forgotten probably the most important one, and that is let's call it a word. Now, a word is going to be anything that is not one of these token types. So all the operations, all of the mnemonics, they're all going to be words. Also, symbols like this are going to be words. So a word is, I'll just write it there, anything else. Okay, great. So armed with this, we can now start thinking about what we want our assembler to be able to do. It needs to be able to read a file and then start producing a list of these tokens. Let's grab this and let's go to our unit tests and let's create a new file. And we're going to call this thing a text assembler because what it's capable of doing is reading uh, the assembly language program from a text file. So we'll add a new file and we'll call it text assembler tests. And here we will first introduce our namespace, and then we will write our class name. Okay, so what shall we start with? We will want to we will want to start this by writing some code that recognizes which one of these tokens shall we start with? Let's start with a number. So we'll create a text assembler, and what we'll do is we will feed the text assembler a big block, the contents of a file. So we will say new text assembler, and we'll pass it in a bunch of bytes. And the bytes are the contents of a file. But in our unit test, we're not actually going to read the bytes from a real file. We're going to just have them inside of our tests, so that we don't have to do file I/O during our unit tests. So let's write the test sample is going to be um, the number 0, like that. And so we'll create a text assembler, and what we'll do is we'll take the system.encoding, and we'll say get bytes from the test ASM. So that will give us an array of bytes. Good. So that we've initialized our text assembler now. And then what we want to do is then say var token equals tasm dot get token. Okay, good. So now we need to implement the text assembler class, which is going to be over here. And as usual, we have our namespace and then our class. Let's go back to the unit test now. And we need to resolve the namespace that we're using. Oh, my bad, it's using RBFun, like so. And now we can generate a constructor with a field for this. And this is a byte array, and this is going to be bytes. Let's call this bytes. There we go. Let's compile everything as well. Okay. Encoding, you need to specify which encoding. UTF-8 will be, as usual, the way that we encode and decode text. Right, and then the next thing we need to do is implement the method getToken. So let's go there. So how do we implement getToken? Now, without going into a lot of computer science theory, tokenizing files is a well understood technique, and there are many ways of doing it. I am going to go rather low level on this one. I'm not going to be using regular expressions or anything of that nature. I'm instead going to do what regular expressions internally are compiled to, which is a state machine. A state machine is a piece of code that maintains current state, which is representing where the tokenizer thinks it is in the stream of bytes. And then what the tokenizer will do is inspect the next byte that it wants to interpret or understand. And depending on what byte that is, it will then either remain in the same state or switch to a different state or decide that that was the end of a token and return a value to the caller. So our get token function is going to do exactly that. And so its return value is going to be token. And token is an enumerated type. So let's put it over here. And when I write these lexers, I usually declare them with the first token be EOF, which is a special token that means that the end of file has been reached. But the token that we want to return for our unit test is number. So let's go back to our test. So after get token is called, we get a token back. And what we want to do is assert that token is equal to token dot number. And then also we want to assert that um, the text assembler current value property, which is something we'll have to define, is equal to 0. An even better test, of course, would make this a 1. Let's change it to 1 because 0 is often a default value for a lot of variables, and so we might miss our test. Or we might get a false positive. Okay, so we need to define this property. That's a property current value, and by default, it will have the value of 0. Good. So let's embark on get token. One of the things we need to do while we're reading through our bytes, which is the contents of our assembly language file, is remember our position. So we'll have a integer called integer position, and we initialize it to 0 in our constructor. Another nice thing to have is a line number, which is helpful when emitting diagnostic errors to the human who needs to read them and understand where he has introduced a syntax error. Initially, our line number will start at 1 because humans number lines in text files starting at 1. So we're at position 0, which is the very, very first byte of our file, and our line number is number 1. So let's read a token. Now, recall that I was talking about something called a state machine, and that implicit in the name a state machine is the word state. We need to define the different states that we could be in while reading tokens from our input. And so we'll create another enumerated type called state. State will initially start, we'll start with a start state, which is where we're in the middle of, well, we don't know anything really. We just know that we're about to start to parse a token. So when we get a token, we'll create a variable called state, and we'll initialize it to start, or right at the beginning of our parsing adventure. And then we are going to consume input characters from the bytes member variable, which is an array of bytes. So we're going to be reading in from that collection, and then we're going to be analyzing that the individual bytes that we're reading based on the state that we're currently in. And we'll do this in a loop that will be an infinite for loop. So we'll repeat forever, and then of course every time that we have completely recognized the token, we will return that token type to the caller. So that's how we break out of the infinite loop. So the first thing we're going to do then is check to see whether we've hit the end of the file. So if our IPause is larger than or equal to the bytes.length, then we're at the end of or beyond the end of our array of bytes. And so the character that we've read, and let's call this character C, C is equal to -1. Actually, let's call that int then. Otherwise, if we haven't, then we can safely read the byte that we, well, from the array of bytes. So we'll say C equals, that's a redundant cast, but we'll do it just for clarity. So we're taking the, the byte at the position IPause and copying it into our character C. And then we might as well increment our position. Okay, so here we have now consumed a character. Next step is to check our current state. So we'll do a switch statement on our current state. And if our current state is the starting state, well, let's go back to our unit test and see what is the very first byte in our string. It's going to be the space character. Now, space is something that we want to ignore. So if we see a space character, and we are also in the state start, then we're just going to ignore it. So if we see a space, we'll just ignore it. And I'll write a comment here, ignore white space. So all we do is we'll do break here, or even better, continue. What the continue will do is it will push control back to the top of the for loop again, and here we will now read the next byte. And so as you can see, if the file consists of just white spaces, then we will just spin in this loop forever until we reach the end of the file. What happens when we reach the end of the file? Well, if we reach the end of the file, we have to handle that as well. So if we reach the case where we've seen the magic symbolic value -1, that is our end of file marker. At that point, we have reached the end of the file. So then we'll just return to our caller, and we'll return the token end of file. So that will tell the caller there's nothing left to read. You can now stop assembling. If any other character arrives, then we will handle it in our default handler. And for now, we'll call a method called unexpected. And we'll pass in the character that we read. And then that's going to throw an exception. Well, no, we don't want it to throw an exception. What we'll do is we will let me think about this. Let's write another method called skip until. Actually, no. Let's not worry about that. We'll do skip until at a later stage. We'll just do a continue here. So what does unexpected do? It's a method, and the method is going to just write an error message to the screen. It will say console.writeLine, and then we'll say error and some line number maybe. And then unexpected character and then the character itself, and then we'll write the ASCII value as well. And let's write that in hexadecimal so it's a little easier to recognize. Okay, so that will take care of that. Also, if we run into an error, um, we'll have a flag called valid, and we'll set it to false. So that way, if we run into any errors, then valid will be false, and then we won't be able to make any use of this erroneous file. So we'll start with a true, and then if we run into any error, then valid will be false. Okay, so we're written a lot of code here. We haven't really tested anything. So let's test this. We should probably also test that after calling getToken a second time, token2 should be an end of file. And the reason for this is that we will consume white spaces until we reach the 1, then we hit the 1, and then we consume the white spaces after the 1. So now we need to handle the actual 1. So how do we do that? When we're in the starting state and we're happily munching up those white spaces and we reach a number, at that point we need to change a state. We need to create a new state, which is called number, because once we see a digit like 1 or 0 or 9 or whatever, we're in the middle of a number now. So we have to change our state to be to indicate that we're recognizing a number. So let's do that. We'll say that if we run into a 0 or a 1, if any one of those digits appear, then what we'll do is we'll remember the position that we're at, and we'll have to also remember that we need to we'll need to remember the position prior to the position that we're at, because we've incremented past the position where the 0 or the numerical digit was. So we'll say that I begin pause is equal to the current I pause minus 1. And then we don't need to change our state, so that the state is now state.number. And then we go continue. So let's create the new state number. We'll need to create this. It's a field. And now that we've done that, we need to go back to our switch statement and add a new handler for this new state. And again, we'll write another switch on the current character that we've read. So if we hit the end of the file and we've already started processing digits, then we know that we can stop processing and return the token. So here, if we see a -1, then we'll just say return token.number. And if it is one other digit, oh, I've forgotten one important thing. We have recognized the digit, but we also have to remember the digit. Well, we can use this, I suppose. Actually, no, we're going to compute the value of the number as we process it. So let's do that. So we'll have, we'll set current value equal to 0. Actually, we're not. We'll say that the current value is going to be equal to the character that we just read minus the literal ASCII character for 0. So remember our ASCII codes. The ASCII codes are the codes for the text representation of a digit. So what we're doing here is we're taking the text representation of the digit, which is going to be some number between 48 and 57, and then we're going to subtract 48 from it, which is what this 0 that you're seeing here represents. That's not the number 0, that's the ASCII character for the symbol 0. So by subtracting the symbol 0 from the symbol that we just read, we will have a digit or a number between 0 and 9. And that's what we're going to put into the variable current value. And then what we'll do is if we continue seeing digits, so if we saw a 1 and then a 0, what we need to do is take the previous value of the current value and multiply it by 10 because we're now seeing the next digit in a longer number. So we'll say current value equals current value times 10. So that will shift our number to the left by a decimal. And then we'll add the most recent digit, which is going to be C minus 0, like that. And then continue. If the character is any other value, then we're going to have to take our current position and back it up one step because we might be positioned on top of a space or a symbol or any other value, and so we need to take a step back. That's what this does. It will take us a step back because we have read past the number part or the sequence of digits, and now we want to reposition our pointers so that when we call this function getToken the next time, it will not have skipped over a character. And then we say return token.number. And at this point, the current value property will have been correctly updated in previous calls or in previous iterations of the loop. So if all went well, then our unit test should pass. So let's build our project and then try running our unit tests and see what happens. Okay, so the project compiles. Now let's go to our unit tests and run them all. And we have a failure. And why would that be? It's complaining that, oh, it's a copy and paste mistake. We need to check the token 2 is EOF. Let's run that again. Let's hope that that was easy enough to fix. And there we go. We have a green dot. So we've successfully parsed the number. Let's try a longer number. Let's try the number 12. And we expect that to be 12. We don't need to test this anymore. And we'll say long. Not a very long number, but long enough. So let's run all our tests. And then let's think about the next symbol that we would like to recognize. How about something simple like colon? A colon is very simple to recognize. All you have to do is check to see whether it's present. So we'll put a colon in here, and then we expect that get token returns colon, a new token type that we haven't yet defined. So let's go now to our get token method, and we'll say um, we're reading spaces, so we'll be in the start state, and then once we encounter a colon, we will just return colon. It's easy enough. And then we might as well write the unit test for left parenthesis and right parenthesis. Since those are other single token. And also um, I'm going to add a comma here. Remember that I mentioned earlier that we're going to be treating commas as white space in our assembler. That's not generally the case. Typically, assemblers will treat commas as specific tokens, but I have my reasons for doing this. So I will ignore any commas that I see. So both commas before and commas after are ignored. So that means that when we run our unit test now, this will fail because it will try to recognize the comma as something and will be treated as an unexpected character. So we'll need to go in here and say that if we see a comma, we will just ignore those. But if we see a left parenthesis, we need to return an L-paren token. And when we see a right parenthesis, we'll return our R-paren token. Good. So if we see one of those, we return L-paren. Oh, token at L-paren. And then if we see its counterpart, we will return a R-paren. Like that. Let's go back now to our unit tests, and let's just put those, I'll just call this test parens. And so we'll assert that the first token is an L paren, and that the second token, token 2, is our right paren. That should take care of those two tokens. I think those were the only. We're taking care of white space, except for tabs. Let's add support for tabs in our parser or lexer. So ignore tabs. Okay. What other symbols are there? So we've done L parent, colon, white space, and decimal numbers. Good. So let's run our unit tests, make sure that everything is still running as expected. And everything looks good. So what else can we do? Well, let's recognize a binary number now. So remember that the binary number is a special case where we start with a 0, then we have a b, and I think we're going to allow lowercase or uppercase b here, and then that b is followed by 0 or 1 binary digits. Oh, well, one or more, 0 or 1 is what I'm trying to say. So that's what makes a binary number. Let's go back then to our test here, and let's write a very simple binary number. And we'll we expect this number to be recognized. And the token type is going to be number still. This is a number after all. And its value is going to be 1. Good. And is equal to 1. Good. Now this will fail with our current code because we are happily plowing along, and if we see a B after a 0, we'll happily stop and return a 0. So if we run this unit test, we'll get the current value is going to be 0 and not the expected 1. So how do we fix this? Well, remember that we've recognized a 0. By recognizing a 0, we switched the state called number, and then when we read the next digit, that is a B, then we need to add a case for that. We need to say if we see an lowercase or an uppercase b, we've seen a binary digit. And now we need to introduce a new state. So we'll say um, state equals state dot binary number. And we also need to insist that there must be at least one binary digit. So I'm going to call this binary number start to indicate that we've started seeing a binary number. And then we continue. Now we need to handle the new state binary number start. So if we've seen a binary number, and if we then do not see a 0 or a 1, then we have a syntax error because we will be in a situation where we've seen 0b and then x or left paren or something. This is not valid, and so we need to indicate or cause an error. So what we'll do is we'll say if the number is a 0 or a 1, well, if it's a 0, then we will just take our, we'll do it the same way that we handle the decimal digits. If it's a 0 or a 1, then we will take the current value and initialize it to the character that we read, which is either a 0 or 1, and we subtract the symbol for the ASCII digit 0. So this will convert a 0, ASCII 0, or the ASCII character 0, into the number 0, and an ASCII character 1 into the number 1, and we'll feed that into current value. But then we need to change our state again. Our state will now be state binary number. So we're leaving the state binary number start. But any other digit or any other letter after a 0b will be invalid, and so we'll write unexpected character and then continue. So now we need to add another case. And that case is going to be the binary number case. So at this point, we have seen at least one 0 or a 1 after a leading 0b, and so now we can be a little less draconian. If we see another 0 or 1, Then we will continue accumulating the zeros and ones. And what we'll do is we'll take the current value and multiply it by 2, and then add the next digit to the binary number. And we'll stay in the same state, so we don't need to update the state variable. But if we instead see anything else, then what we'll want to do, well, we need to handle the end of file special case anyway. So if we hit the end of the file, then we have ended the file with a binary number, so we will return um, token.number. But if it's anything else, then we need to back up one step, just like we did for the decimal numbers. And then we'll say return token.number, like so. Okay, let's run our unit test now. And look at that, success. Let's prove it to ourselves by taking a longer number. Let's take the binary number for, let's use this binary number, which is the number 10 in decimal. And let's make sure that that also runs. Indeed, it runs. So now we've knocked that out. So we've done binary numbers. Now we might as well do hexadecimal numbers. Let's do those. We're picking up speed here. These tokens are not that hard to recognize. So we'll do a hex number. So we'll take 0xf, which is 15 in hexadecimal. And that's going to fail now if I run it, because obviously we're not recognizing 0x. But just like we did the recognition for 0b, we will now recognize 0x. So if any of those two digits are or letters are found, we switch our state to state hex number start, and then continue. And then we have to add a new case for hex number start. It's going to be very similar to binary number start. We could steal it and then modify it. So if we see any one of the digits, if it's any one of the decimal digits, then we're going to adjust that. So we'll remove the ASCII value of the 0 digit from the character that we read. This will give us a number between 0 and 9. But we then also have to add the case for the uppercase letters. A, B, C, D, E, and F. And recall that these hexadecimal digits symbolize the numbers 10 through 15. We also need to change our next state to hex number. So in the case of one of these larger numbers, then we need to subtract the ASCII code for the letter A from the character that we just read. But that's going to give us a number between 0 and 5, and we need to adjust that by 10. so that the number becomes a number between 10 and 15. That's what that shift does right there. And then we also shift to state.hex number. And then we have to handle lowercase letters. And those are handled this way. And that should take care of that. So in either case, if it's a hexadecimal digit, then we accumulate it into our current value and then continue. Otherwise, if we saw 0x but then no hexadecimal digits, then we are in a bad place. So we raise the unexpected and emit an error. Next thing we do is we implement the hex number case. So that's going to be case hex number and no longer a start. Now we've already seen one hex digit, so we want to take current value multiplied by 16 this time, and then add the little residue here. And the same thing goes here. And here as well. Good. That should take care of hexadecimal numbers. Let's make sure that we have unit tests for both a short and a long hexadecimal number. And if it's a long one like this, FF, that should be 255. Let's run all our tests. And my computer is very slow. Very slow indeed. I didn't cancel anything. Let's run it again. Oh, maybe we we are looping infinitely here. No, I don't think we should be looping infinitely. Oh, right. At the end of a valid hexadecimal number, we need to back up one step to continue with the next. So instead of this default case, we have that default case. Okay, let's try that again. Good. So now we're recognizing all of these tokens except for word. So what is word? Well, word is anything else I've written here, but maybe we should be a little bit more, let's be more accurate about what a word could be. So here's some examples of words that we would like to handle. So word is the word "adai," for instance. The word hello underscore world should be a word. Underscore hello should be a word. And I also think that hello 1 2 3 underscore should be a word. So we're going to define a word as a token that begins with either a letter or an underscore, and then followed by letters and underscores and digits, decimal digits. So that is the definition for a word. So if you write it as a regular expression, you might write it as A through Z underscore, and then of course capital A through capital Z, and then underscore, followed by A through Z underscore 0 through 9 star. That is what a word is. So let's go back to our assembler tests then, and let's write our final token type, which is a word. Let's let that word be B. And we're going to add a method called get string, or get token string, and that should be equal to the letter B. And then we want to handle the case when the token is an underscore. So this is a valid word, and this should also be a valid. And how do we proceed? Well, at this point, we could here, in our default case, the default case inside of the state start, we would say if is ASCII letter C, or C is equal to the underscore character. If that's the case, then we want to remember where we started, which is IPOS -1. And I just realized we never used this, so we can get rid of that line of code. But here we want to remember our previous position, because the increment that we do here will skip past the position where we'd recognize the letter, so that we're backing up one step. And then we're switching our state so that we now have a new state called word. And then we continue. If it's anything else, then we are in an error state. Good. And then we have to add a new state for word, or a handler for that state. So let's do that. And we'll do another switch. And here we'll say if we see a -1, then that's the end of our identifier. Return token.word. If we see, oh, and then if we see ASCII letter or digit, handily provided to us by the .NET runtime. So if it's either a letter or digit, or the character is an underscore, then we will continue. We will proceed consuming characters. Otherwise, we've reached a character that is not a valid word character, but we've already seen a few because we're in the state word. So what we'll do is we'll back off one step, and then we will return token.word. And then our function getTokenString, which is intended to be called right after you've recognized one of these tokens, it will return encoding.utf-8 getString starting at I begin position and in the buffer this.bytes, and we want to count how many letters. We want to take the ones between I pause and I begin pause. So that will give us the string that we have been recognizing. Okay, I'm happy with that. Let's see if it works. Okay, so we have a failure. We have multiple failures. Oh, copy and paste. This is not a number, this is a word. And then all of our tests are passing. Wonderful. So now we have an assembler tokenizer that can recognize all the tokens except for comments and new lines. And I will write that code in the next episode because it's been an hour of rather boring programming. But the interesting part is that now we can recognize most of this file. And so next time we will deal with the final tokens, which are the string tokens and the comment tokens, and then what to do with new lines. Once we have tokens, then we can move to a higher level of abstraction. We can start thinking about how do we recognize machine code instructions like this one. And if you think about it, it shouldn't be too hard to understand that what we're expecting then is to find a word followed by one or more numbers. So if we can recognize that, a word followed by three numbers, then we have um, a possible add I instruction in our hands. But as I said, that will have to wait until next time. Thanks for watching, and see you then.